Hello. This little thing is getting pretty far along here. I've got the DDS module mounted. I've already went through a couple revisions of the firmware. This is version 4 currently, to get a couple little bugs worked out of the code that I've got, and got switch mounted or hooked up to the unit. The only thing I haven't filled out yet is the output stage to drive the B and C jack on the front, but I've got it to a point it's almost what you'd call workable and about ready to be mounted into the enclosure and stuff that I've got for it here. But I'll give you a quick overview of what the display shows and everything here. Zoom in. I decided to take and just put CPS for cycles per second, old fogey style frequency measurement. I've got it where you just press the button to increment your tuning step, going up 2 megahertz stuff. And a lot of people generally like to artificially limit the tuning range of the module, how far the controller will calculate the tuning word for, but I decided to leave everything basically open on the firmware so I can crank in the frequency all the way to 99 megahertz, even though of course the aliasing and stuff pretty much wipes everything out past 40-50 megahertz, but I can still crank in the tuning word for whichever frequency I want, from 0 hertz to 99,999,000 whatever megahertz, and see 9999 all the way to 000. And I've got a little bit more functionality into it than that, but it took me a couple of things to straighten out on the firmware. Is if you take and go to the end digit and press, hit it straight here, and not wanting to cooperate. There you go. Press one more time, then it brings up a sub menu, which you can select a sweep frequency program. It'll take and sweep from the base frequency that you got up there, and either a no sweep program, which is a 0, or a 10 kilohertz sweep program. Sweep program 2 is 100 kilohertz from the base frequency up 100 kilohertz, and sweep program 3 is base frequency up 1 megahertz, and the microcontroller takes and sweeps. Where at first, way I wrote the firmware is it first calculates the base tuning word, which in of course this is going to be straight 0. Then it increments the tuning, recalculates it 100 hertz higher, then loads that, then 100 hertz higher and loads that. And generally it will scan the 1 megahertz of bandwidth in 100 hertz steps about in 3 seconds, or about 10,000 tuning steps. It'll calculate the tuning word for, load them, and proceed on to next. About total of 10,000 tuning steps. Yeah, that'd be exactly 10,000 tuning steps in about 3 or so seconds. And it repeats that infinitum as long as you got it set to sweep program 3. And neat little feature on this is I can leave it set in sweep program, then go back to the root frequency, then adjust the root frequency while it continues to sweep 1 megahertz up above that. And what's good about that is I can take, if I'm looking for like the bandpass frequency of a filter network and like it's not labeled or whatever, I can take and set this on 1 megahertz sweep and slowly work up the band till I find about where the bandpass is. Then I can take and narrow down the sweep range and get a better idea of the functional capability of a filter. Stuff that's what I got in mind. That's a little sweep frequency program. And 0 here, set it back to straight non-sweep. And just press the button to increment through. And I'll show you on the oscilloscope here in a second what the actual sweep frequency output is on this here. And for a little bit more background in the firmware program I wrote, it should be accurate with the actual tuning word calculation within 1 hertz all the way up to 19 million, whatever the operating frequency is, because the way I've got it set up, it calculates the tuning word down to 40 places, 40 binary places, and then truncates the last 8 digits and just loads the 32-bit tuning word in. But it actually, the microcontroller way I got the firmware set up, actually calculates the tuning word to 40 point precision, then truncates the last 8 bits and loads the 32 highest order bits, so there shouldn't be any rounding problems or anything stuff. And I'll also hook it up to frequency counter so you can see what the actual stability is or accuracy is of the total module itself, including the built-in crystal oscillator and stuff here. Let's see here. Here's the oscilloscope display, of course, at 2 megahertz. Let's get it centered here. And when you crank it up to 16 megahertz or so, but crank it down to about 0 hertz, 1 cycle per second. Alright, now set it to sweep program. It's set at 0 hertz and go up to there we go. Sweeps from 0 cycles per second all the way up to 1 megahertz. And again, that is in 100 hertz steps. Tuning word calculated in 100 hertz steps and loaded to the DDS module, which the calculating speed, as I said, is probably about 3,000 tuning steps calculated per second, which it's running off of a 3.8 megahertz oscillator clock, or oscillator crystal. So of course, with the divide by 15 cycle time on the 8048, with the calculating logarithm I've got, yields about 3,000 calculated tuning words per second. If I cranked it up to 12 megahertz crystal, I could get probably around 10,000 tuning words per second, which if stuck it down to 10 hertz steps, then you could probably go 1 megahertz sweep and 10 hertz steps every 10 seconds or so if you wanted to go to that. And now go to the 100 kilohertz sweep. Then the about 10 kilohertz sweep. Gives you an idea of what it looks like from 0 to 10 kilohertz and back to no sweep program. Give it normal straight frequency. I get the sync back here. I have 50 kilohertz. Now I'll hook it up to a frequency counter here, or a couple frequency counters, and get an idea of about the offset or the error in the reference crystal of the DDS unit here. Alright, let's see here. Alrighty, this is a frequency readout. The DDS unit is set to 1 megahertz exactly, and getting a readout of 1 megahertz, 6.7 hertz off, at 6.7 hertz high stuff. That's with a program frequency of 1 megahertz on a relatively calibrated frequency counter. And if you shift it to 2 megahertz, wait for the counter to catch up here, we show about 13.3 hertz off. So it's running around 6 parts per million, 6.5 parts per million high stuff. That's on the Heathkit. And if I go to a more accurate frequency counter here, let's see here, and to shift it back down to 1 megahertz. This frequency counter here has a vacuum encased time standard, so I've checked it before with WWB and other stuff, and it's pretty much dead nuts on. So it's showing around 6-7 hertz offset. If I give it a long 10-second gate here, we'll get the exact 1/10 of a second accuracy. 6.5 hertz high, which is about the same thing the other one was reading. Stuff. Let it cycle the gate again. Yeah, 6.5, 6.6 hertz high, which it seems to be relatively constant. If I take my finger and put on the crystal, cool it down a little bit, you will see the frequency drop just a little bit down closer to, yeah, see it's dropping down to 4.2 hertz high. Stuff, and what it looks like is that shift remains about constant through the tuning range around, when it's warmed up, operating temperature around 6 parts per million high on this one. Of course, everyone's going to be different. Go back to this one here. Relatively fast gate. And crank up the frequency some. Go up to 10 megahertz and see if that holds, you know, around 6.1, 6.2 meg high. Let's go back to a long gate time, and of course we're going to see overflow flag here. Yeah, it's got a 61.6. Let's see it cycle over again. It's 62.2 hertz high for a 10 megahertz signal. Of course, you can take, and if I wanted to, I could get an average idea of its frequency offset or frequency error, and then recalculate the tuning words that the firmware uses to calculate the recalculate the tuning formula for what the firmware uses to calculate the tuning word, and I could zero that error out to a degree. Stuff, basically shift the tuning word about 6.2 to 6.3 parts per million low, and then it'd be pretty much dead nuts on if you was really worried about that level of accuracy, but I'm not. So go relatively fast gate and put it on a sweep program to 3, and you'll see it going up in frequency from the 10 megahertz base frequency up to 11 megahertz and then cycling back. And it's on its sweep program, so alrighty, it's about where it's time to put it in a case with its connectors and make up a power supply for it. But beyond that, it's pretty much a completed functioning unit. So take care. See you later.